Hi. To start this new topic, which I've called rock forming processes, which looks at taking our understanding of metamorphism and sedimentary processes just a step further than we did at AS level, I thought it would be worthwhile to spend a little time just thinking about what we actually mean by metamorphism. Okay. This is a metamorphic rock. How can we tell? What is it about this rock that reveals its metamorphic origin? We need to think about what we actually mean by this term metamorphism, really, to understand that. Metamorphism means change. A combination of heat and pressure is applied to a pre-existing rock, and it changes as a result of that. But what changes? We have textural changes. You can see in this particular rock we have some foliation that's developed, an alignment of crystals that have grown as part of what we call solid state recrystallization. We'll talk more about that in a moment. But there is a distinctive metamorphic texture to this rock that's formed as a result of pressure being applied. So crystals will grow at right angles to that pressure. If we look carefully, we can actually see two lots of foliation within this as well. As well as texture, we also have the minerals that we find in the rock. In particular, this rock has got a garnet crystal, a large, what we call a porphyroblast of garnet, the big dark crystal dominating this particular slide. As well as the garnet, which is a distinctively metamorphic mineral, we also see the very brightly coloured mineral that's picking out that foliation. Now in this case that's muscovite mica. Now we do find muscovite in other types of rock, but finding it in these aligned foliated sheets is distinctive of metamorphism. And this mineral has grown, as well as the garnet, because of a recombination of elements within the rock. So new crystals have grown, either along in sheets to form these foliations, or growing within the rock to form that big porphyroblastic garnet. So we can tell a lot about the metamorphism by looking at these features. Now, there are some distinctive metamorphic minerals. This is a list of some of them. And we can see that at different temperatures, we'll get different types of mineral growing. So at lowest temperatures, we'll find a mineral called chlorite. At highest temperatures, we get pyroxenes, which is another word for augite. But there's a progression of these minerals. So the collection of minerals that we find within a metamorphic rock will tell us the temperature conditions at which they formed. If you like, they're paleothermometers. Now the reason for this is that these minerals, the bonds within them, the bonds between those elements, will be stable at different temperatures. So we can think about, if you like, a stability field, as a range of temperatures at which these minerals are stable, therefore at which these minerals are going to form. We can tie that in with this graph that we're familiar with. You'll have seen this graph already in the course, where we have these different areas on this temperature pressure graph that show us where these different processes occur. Can you remember what these conditions are, where we find the different types of rock? We've got contact and regional metamorphism labelled up. Where would we find, for example, igneous rocks on this graph? Where do we find sedimentary rocks? What's the significance of that limit of metamorphism in the left-hand side? Can you annotate your copy of this graph with what you remember about metamorphism already? We can see as well this progression of different rocks. Remember that phyllite and migmatite aren't on your specification. You don't need to know them, though they do exist. What's different about those rocks? What's the difference between a mudstone and a slate and a schist and a gneiss? How does that tie in with what we've said about texture and composition? Now we can develop this a little bit further. This is a graph. We're going to visit this in a little more detail a little later on in this topic. And this shows us the stability fields of a particular type of metamorphic mineral. These are all different forms of aluminium silicate, Al2SiO5. And there are three different forms of this. A mineral we call andalusite, that you'll be familiar with from your mineral data sheets. Another mineral called kyanite, label K on this graph. And a third mineral called sillimanite. All these are metamorphic minerals, but you can see they form in different pressure and temperature conditions. That can help us understand the pressure and temperature at which metamorphic rocks form. We can even take that stage further and start thinking about how metamorphic rocks actually get buried and how they come back to the surface. And the minerals that we find, and certainly the versions of these minerals that we find within these rocks, will reveal what actually happens during metamorphism. More about this when we look at metamorphic pathways. Okay, to conclude, as we look at sunset over the Callanish stones in the Outer Hebrides, a spectacular stone circle. Each of those stones, of course, are 3 billion year old pieces of gneiss. Different temperature and pressure conditions will form different textures, different minerals, and as a result, different types of metamorphic rock. We need to dig deeper into that idea to understand how we can interpret these pressure and temperature conditions from the evidence that we find within the rocks. And the following lessons are going to be getting stuck into that. I'll see you then.